Hello and welcome. In this video, we're going to talk about how to find the arc length of a smooth curve and the total distance traveled. Let's go ahead and jump right in. So let's first talk about what we already know about length. And what we already know about length is the distance formula. So we can say that the distance is the square root of x2 minus x1 squared plus y2 minus y1 quantity squared. So if I wanted to approximate the distance of this red piece here, or the length of this red piece, I could use a secant line and I could approximate that distance or that length. Now, that's not going to be a very good approximation because it doesn't look a lot like the line that we're looking at. But what if I broke it up into a couple of pieces? So what if I found this length and then this length and maybe this length, and I broke it up into multiple lines? So the more lines I break it up into, the better the approximation is going to be because I'm getting closer and closer and closer to that actual length. So if I just am looking at, let's say from some A to some B, if I'm looking at an infinite number, that's going to lead us to integration. So the more line segments that we have, the better the approximation. That's what leads us to the idea of integration. So I'm going to do a real quick version of this proof to try and just get you to understand conceptually where it comes from, where the formula from arc length comes from. But the key ideas here, we have to be talking about a smooth curve that we're partitioning between the interval from A to B. So let's go ahead and write down some thoughts here. We're going to first talk about looking at the sum of all of those lengths added together. So we could be looking at the sum of all the rectangles from I equals 1 to n of that distance, the square root of this change in x squared plus the change in y squared. Well, we could also now multiply, because our ultimate goal is to get everything in terms of x. We're going to multiply this term by delta x over delta x, which we're allowed to do because that's the same thing as multiplying by 1. So let's look at what that gives us. And let's actually square that. And again, this is not the most intuitive proof, but I think conceptually you can understand the more triangles or the more segments we have, how this leads to integration here. So this is going to be still times delta y squared. So I haven't changed anything. I multiplied by delta x squared over delta x squared. Now I'm going to rewrite what's inside so that I can have the change in y with respect to the change in x. So I've manipulated the way that that looks now. Again, I haven't changed anything. If I simplify the red and the blue, I would get back to my delta x squared plus delta y squared on the inside. But now that I have this, what I have are 2 delta x squareds, which I can take the square root of delta x squared to just give me delta x, and I can pull that out in front of the sum. So that's going to get us here. Now, if we want to have an infinite number of rectangles, we're going to look at the limit as n goes to infinity of this same approximation. And then since we're talking about a smooth curve, the derivative exists everywhere, which means MVT guarantees that there is a value such that the derivative is equal to f prime of this particular delta y over delta x, which means we can actually, moral of the story, we can substitute in f prime of x or f prime of the value we're looking for to write this as a limit. So I can't use x here because I need something, I need this to be changing as I is changing, so I'm just going to call that c sub I. Now if I wanted to change this to an integral, this delta x is going to become my dx. My integral is going to become the integral from wherever we're starting a to wherever we're ending b of the square root of 1 plus f prime of x squared dx. So that's where this formula comes from. No one's going to be assessing you on the proof here. It's just good to know where it comes from. But even just conceptually understanding that the infinite number of little pieces that we're adding together, that length, would give you the exact length of the curve. So let's look at this in the right formation. So let's formalize this now. If a function y equals f of x represents a smooth, continuous curve, it's got to be continuous and smooth so that the derivative exists, then we can find the arc length using this formula. Now you need to know this formula, but many of these problems will be problems that you could do on your calculator. So what do you need to do to use this formula? You need to figure out what the derivative is, you need to find the bounds, which will typically be given to you, and then you need to plug everything in. So let's go ahead and look through some examples. So for number 1 down here, the first thing we need to find is what the derivative is. So y prime is going to be 1/12 times 3 over 2 times x squared plus 8 to the 1/2 power times the derivative of the inside, which is 2x. So this is going to be, if I simplify all of this, 1/4, or I guess I could say x over 4 times x squared plus 8 to the power of 1/2. Now I can substitute that into the formula. The bounds are the length that we're finding, so from 1 to 4 of the square root of 1 plus x to the 4th times x squared plus 8 to the 1/2 power, that whole derivative squared with respect to x. Now you could actually do this problem without using a calculator. It would require quite a bit of algebra, but not too extensive. But you can go ahead and grab your calculator. Remember that you're pressing Math 9 to get the integral. Don't forget about your square root and be careful with your parentheses. This should give you 8.25. Okay, number 2. Again, what we need is y prime. Well, the derivative of sine is cosine. So the length from 0 to pi of the function y equals sine of x is going to be the square root of 1 plus cosine squared x. And go ahead and grab your calculator. This is going to give you 3.820. All right, we're going to look at a few more examples, but that's really the only thing we're covering in this video is using that arc length formula. Okay, so we're going to use a calculator on 3, but we're not going to use a calculator on 4. And I actually encourage you to pause the video and work through both of these examples on your own, and then unpause the video and see how you did. Suppose that g of x is given here on the interval from 0 to pi. What is the length of the curve on the interval? The curve y equals g of x on the interval from 0 to 7. So the first thing we need to figure out is what is g prime of x, and that's just going to be using the second fundamental theorem of calculus. So I'm going to get the square root of sine of x, and then I just need to plug that into the formula. We're looking for the length from 0 to pi over 7 of the square root of 1 plus the square root of sine of x, quantity squared dx. And then you could simplify this to just be 1 plus sine of x on the inside, but since we're using a calculator anyways, I'm going to leave it. This should give you 0.495. All right, no calculator on number 4 here. Let's work through this one. So the first thing that we're given is that g of x is the square root of 3x, and f is the antiderivative of g. So f prime of x is going to be equal to g of x, which is the square root of 3x. For part B, it says find an expression for the length of the graph from x equals a to x equals b. Well, the length from a to b is going to equal the square root of 1 plus the square root of 3x squared, which I'm just going to write as 3x dx. Now, notice this problem doesn't say that we can use a calculator, so we're going to do it without. If a is 0 and b is 8, find the length. So the length from 0 to 8 of the square root of 1 plus 3x dx. I'm going to reverse the chain rule here. The derivative of the inside function is 3, so I need a 3 here, which means I need a 1/3 here. Now you can use u substitution if you want to, just make sure you change the bounds. So this is going to give me 1/3 of 1 plus 3x. It was to the 1/2 power. If I add 1, it's going to become to the 3/2 power times 2/3. And we're going to be evaluating this from 0 to 8. Let's come over here and have some more room. So this is going to be, the length is going to be 2/9 times, If we substitute in 8, we're going to get 1 plus 24 to the 3/2 power, minus, if I plug in 0, I'm just going to get 1. 25 to the 3/2 power, well, that's the square root of 5 cubed, which is going to be 125. So this is going to be 2/9 times 125 minus 1, 124, which is going to be 248/9. Okay, let's look at 2 more examples. All right, I'm going to encourage you to pause this video and work through both of these examples on your own, and then unpause the video and see how you did. So hopefully you've had time to work through this on your own. I just created a quick sketch of what's going on with our 2 functions, f and g, and I'm going to go ahead and figure out mathematically where they intersect. So x squared minus 4 equals 5 when x squared is 9. So x is going to be plus or minus 3. Those are going to be our bounds on our integral. The total length that we're looking for is going to be the integral from -3 to 3 of, let's look at this piece here. So the quadratic, the derivative of that is going to just be 2x. So the square root of 1 plus 2x squared dx. Plus, we're looking for the whole perimeter, so we also need this length. Well, this length is just the length across this line, which is going to be plus 6. So there's our integral. And if we actually substitute that in like we're supposed to for part B, this is going to give us a total perimeter of 25.494. Okay, the last question, the very first thing that I would do, and we got to use the multiple choice to our benefit, is we're looking from 1 to 3, so all of these are covering that. Our function is 1/2 x cubed, so the derivative is going to be 3/2 x squared. So I'm looking at the length from 1 to 3 of the square root of 1 plus 3/2 x squared squared dx. And what I notice first is that this answer isn't there. So I'm going to simplify and see what I get then. 1 plus, this is going to give me 9/4 to the 4th dx. So looking up, I'm going to eliminate a and b because there's no way that I should be getting x to the 6th. I should be getting some variation of x to the 4th here. And between these 2 answers, now I need to figure out what kind of manipulation happened to get rid of what's here. And my first thought is maybe I need to just get rid of this 1/4. So if I factor a 1/4 out, that's going to give me 4 plus 9x to the 4th. That 1/4 can come out in front as a 1/2, and that answer is there. So C is going to be the correct answer here. So key ideas in this section: finding the length using the arc length formula, make sure that you're using a smooth curve, make sure you're finding the derivative, and that you're plugging everything in clearly. Draw pictures as needed to help you out. Go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.